Welcome, this is lecture number 27. In this lecture, we are going to talk about circuit averaging technique and equivalent circuit model. So, the concept which will be covered are circuit averaging technique, small signal model with assumptions, 3 terminal model and average switch model, then equivalent circuit of switch mode power converters. So, first we need to understand what is the objective of AC modeling. So, we are talking about a switching converter. Here I am showing an example of a synchronous buck converter. Here we have already seen that this converter is operated by a periodic pulse, that means switch signal, gate signal, and the switch is turned on and off in a periodic interval, and there are two switches S1 and S2. It has a nonlinear like on off characteristics. Now, for modeling like a AC modeling, the small signal modeling, we need to neglect the switching ripple component, because we need to extract the average dynamics. We need to ignore complex harmonics information as well as the sideband information. We are only interested in finding the term or the frequency which is associated with the excitation frequency. That means, if we excite the converter, like it is already running by a fixed frequency clock, but if we excite the duty ratio with a modulating frequency, we are interested in finding what is the response of the converter due to the injection of the modulating frequency, and we want to find out what is the component corresponding to that modulating frequency. Then we want to predict low frequency variation behavior and we want to predict low frequency variation in duty cycle. Because we are talking about a switching converter, and this part we have already discussed in state space averaging, and if we talk about the duty ratio where we are going to operate the switching converter using a pulse width modulation technique, where the time period is fixed and the duty ratio under steady state it is fixed, but if we consider a time varying duty ratio, where the duty ratio is consists of one steady state quantity plus one excited like a small component AC component, which is the sinusoidal excitation, and the assumption the amplitude of excitation is much smaller than its steady state value, and of course, the modulating frequency or the excitation frequency is much smaller than the switching frequency. With this assumption, if we take the behavior of the actual switching converter, we can extract the average dynamics and we can ignore the switching dynamics or neglect the ripple information, provided that the frequency ripple frequency or the switching frequency is much faster than the excitation frequency. And we know, if we obtain the power spectrum of the output voltage, or if you take the spectrum of the output voltage, then we will get a DC component where it is like a 0 frequency, where we will get the average value of the DC voltage, and then since we are exciting the duty ratio with a modulating frequency, we will get a side lobe omega m and also its harmonic. Similarly, this side lobe will be created. So, this will be created modulating frequency and harmonics. Similarly, switching frequency and sideband, this is the switching frequency component, and harmonic content of the corresponding to the switching frequency, and around that harmonic content also you will get side lobe. Since we are considering the omega m to om to be very smaller than switching frequency, so these lobes are very close to each other, and we are particularly interested in this particular frequency, which is the excitation frequency or the modulating frequency. Now, why circuit average is needed? Because any averaging technique, we try to eliminate the harmonic information, but if we take a generalized averaging technique where we can also incorporate the harmonic information, but here we are talking about standard or the traditional averaging technique, where we eliminate the harmonic information and we take only the average information of the the dynamical equation. So, we take only the average dynamics, by averaging over a cycle switching period. That means this models, as I said, is valid only up to the half of the switching frequency. Then we will replace switching part of the converter with their average quantity. And then how do you model? So, the modeling technique we discussed so far, state space average model, which is proposed by Middlebrook from Caltech. It is a very well known and is a very frequently used technique. Then 3 terminal switch model, it was proposed from Virginia Tech. And then finally, we want to write even the state space model can be framed into a canonical form to obtain an equivalent circuit model. That means, using a transformer, whereas the 3 terminal model can be used to directly obtain the equivalent circuit. Okay. And we will see that in the previous lecture we discussed about state space average model, which is straightforward, but it is much more mathematical, like to obtain all the state space model, then we need to obtain the Jacobian small signal perturbation and so on. But in equivalent switch average switch model, under certain consideration, if we average out, if we obtain the average switch model of the switching part only, the rest of the circuit like a RLC part and other part we are not going to touch it. And in this method, the second the average switch model, we will see it has the benefit, because if we incorporate some additional dynamic element, the switch model will remain same, only the dynamic element will be added. So, the system the same approach, only the circuit has to be expanded with an additional element. But in state space average model, we need to rewrite the equation again for the additional dynamic element, and then we have to follow the step for state space averaging. So, in that way the circuit averaging technique is more kind of a generic model. That means, it is more like a modular approach, where the additional element can be easily incorporated into the model without re-deriving the equations. Now, if we take the PWM switching converter, the switching particular the block which is responsible, like this is we call it as a switch node voltage. This is a switch node voltage, and this voltage changes like a square wave, not square wave, is a pulse width modulated wave, and this will create an excitation for the RLC circuit. And then you can, by controlling this switch node voltage, we can actually control the output voltage in average sense, and it will also generate harmonic terms. And if we design properly this filter element, then the component associated with the harmonic and the switching component can be substantially reduced compared to its average value. So, in this model we take one active switch node, common node and the passive node. Although this the 3 terminal model, this is important, but we are not going to discuss detail about this different terminal and their detailed explanation. We want to extract the basic modeling information out of this 3 terminal or the average switch model. So, this model you can apply to buck boost and buck boost by suitably considering the 3 active, common and passive node terminals. Then what next? The next, if we take this 3 terminal model, for this, for example, this resemble the switch network of the buck converter, we can write a DC model where the S will be replaced by capital D and S bar will be replaced by D bar, where D bar is the 1 minus D. Also, we can take AC model where S will be replaced by small d and S bar will be replaced by D bar, and that is shown here, the average quantity. But this is not complete, we have to write the current and voltage equations, and we have to take into account current and voltage expression associated with this switch. That means, what is the current entering into this network and which is the leaving, like which is coming out. So, basic AC modeling approach, if we take a buck converter, first one approach which is known as circuit averaging technique, in which we want to first write or draw the equivalent circuit for different switch configuration. For example, when the switch is on, this is the equivalent circuit. So, this circuit is the equivalent circuit when S is in one position, that means S is 1, or basically this is in the position 1, is connected to position 1. Then from this model subsystem, it is simply like RLC circuit. We can write down all the equations corresponding to this switch state. Then out of this equation, there are two dynamical equations, like one is the derivative of the inductor current and the derivative of the capacitor voltage. In this configuration, if we continue for longer duration, so this duration the current will keep on increasing, right, and capacitor voltage depending upon the inductor current magnitude. So, it will also have some ripple information, and we are approximating using, that means if we take the voltage across inductor and we can take their average quantity. Here the assumption is that if we take the instantaneous output voltage, it consists of both average as well as the ripple information, but here we are only considering the average quantity, we are ignoring the ripple quantity. So, ripple is approximated to be very small. Similarly, the capacitor current also we can use in terms of their average quantity, which corresponds to the actual instantaneous states. That means, the instantaneous output voltage and the instantaneous inductor currents are replaced by their average quantities. So, this is small ripple approximation. Similarly, we can take the other switch state, that means, when the switch is off or it is in position 2, then again we can write down the dynamics of the inductor current as well as the capacitor voltage. And here also under small ripple approximation, the instantaneous current and the instantaneous voltage can be replaced with their average quantity. That means, the output voltage instantaneous and the inductor current instantaneous are replaced by, this is the average quantity, like all are average quantity. That means, we have ignored their ripple information. Okay. Then what we will do? Then that means, inductor current waveform, if we take for example, this is the inductor voltage waveform, okay, VL. So, inductor voltage waveform, if we take the average over the inductor voltage, it can be represented by, that means, instead of, if we ignore this ripple information and take just the average quantity. Similarly, the average quantity during this cycle, it can be approximated by this. So, this approximation makes sense, or it is somewhat, it is reasonable when we assume these ripples are, the effect of the ripple component is negligible. Similarly, the inductor current over one cycle, we can take the average value, and this can be considered, that means, we are talking about this average inductor current dynamics. One switching cycle, it can be represented by this. Then what we will do? The average capacitor current also we can obtain. The average capacitor current, you see the capacitor current is nothing but the inductor current minus the load current. Okay? Now, the average inductor current, that means capacitor current during, so here the inductor is always connected to the capacitor. So, it will be common for both on state and off state. So, we can take the average and then sum of this duty ratio, which is 1, and which is nothing but the average capacitor current expression. Similarly, average inductor current, it is same as the average input current, it is same as the, we are talking about the average inductor current over this period, it is same as the average inductor current during the interval, which is sorry, it is not the average, I think this is the input current when the switch is on, it is same as the inductor current when it is in position 1, and it is 0 when the switch is off. So, if you take average input current, then average input current should be equal to D into average inductor current. That is because it is only inductor current, input current is equal to inductor current when the switch is on and it is equal to 0 when the switch is off. Yes. So, average quantity is written by this. Now, the small signal model assumptions and states. Considering, if we consider the average quantity to be replaced by the DC term and the AC part of term for all parameter, and this process we did it in state space averaging also. Then what can we write? So, this is applicable, that means when we are considering, because we are talking about small signal model where we are ignoring the nonlinear term, that means any product of perturbation should be ignored, and this is only valid when the small perturbation, the perturbations are much smaller than their corresponding steady state values. So, this is the condition for which our small signal model is valid. Then the nonlinear circuit element, that means switching element, will be replaced by their average quantity as well as their linearized quantity, that means, and we will show, and then we can obtain the AC equivalent circuit model. Next, we are going to consider perturbation and linearization. So, we need to obtain the linearized model from its nonlinear characteristics, and in order to do that, let us consider the inductor current average dynamics in a buck converter. Here, the ddt of the derivative of the average inductor current, which is this one, the derivative of the average inductor current, that means this is the average inductor current, is nothing but d times the average input voltage and minus average output voltage. So, now if we write this average quantity, which is equal to steady state quantity plus IL hat. So, all quantities are replaced by their steady state value plus the part of value. So, then we will get right side equation, that means this quantity is coming from here, then this d is nothing but, this is nothing but d, and this is nothing but V in the average quantity, and this is nothing but the average output voltage. Then what we will do? If we expand this, we will get, so this is the steady state term, and if we take differentiation, it will be 0. So, it only will have left side with the small signal part of term. This is our corresponding steady state term, and this is a nonlinear term. That means, this should be 0, it is already shown. This is a DC term, the first order AC term, only part of term, and this is a nonlinear term which is a product of perturbation, and we want to ignore that. This also we want to ignore. Under small signal approximation assumption, this can be ignored. Next, we want to write down the left side L DIL dt expression, and if we rearrange this term, and if we take this term, then we are getting this term. Then if we consider this term and this term, like this term, then this will generate this result, and then if we consider this is this term. Okay. So, we can write down the equivalent circuit. This term is coming here, and since here L DIL dt is also equal to L ddt of IL hat, because we know that DIL dt is equal to 0. So, you can simply put them. So, that is why this is coming L DIL dt, that means it includes both DC and AC information. Then this term is coming here and this term is coming here. Okay. The next, this is the inductor current equivalent circuit. The next we want to write the output voltage or the capacitor voltage. So, the capacitor current average dynamics, we know for a buck converter is this, and if we expand this term, then we can write down this equation. This is steady state term, it will be 0, that we have discussed, and if we rearrange this term, what we will get? So, a DC term, it is the first order term, and you can rearrange I L, that means this term and this term are added to get this term, and this term and these terms are added to get this term. Okay. Then we can write down the equation of the capacitor voltage, and we can obtain the equivalent circuit, and this is a capacitor voltage equivalent circuit. Now, input current also you can write. We know what is the input current. The average input current is nothing but D into average inductor current. So, if we write down, the average quantity can be replaced by their steady state quantity plus part of quantity, and this D can be written as this term, and the average inductor current here is nothing but I L average. Now, if you expand, so we can get, and you will find this is a DC term, this is a first order AC term, and this is a nonlinear AC term, which we have to ignore. Then if we ignore this term, because we are talking about a linearized model, then we can simply approximate this term to get this, and under small signal approximation these equations can be written, that means from here, and then we can draw the circuit. Because this is the total current which is coming, the input current is divided into two parts. This is one current which is here, and this is another current which is here. Okay. So, we can combine together. Another approach we can do, if we take the 3 terminal PWM switch, here if we take a buck converter, here left side if the input voltage and it is the input current, this is a switch model, and this is the inductor current going through, and this is a voltage across, this is a switch node voltage. You see, the switch node V2 is equal to V in when the switch is on, and it is 0 when the switch is off. So, then we can get the average voltage V2 in terms of D into average V1, and here again we are ignoring the ripple information. Similarly, if we write the inductor current average value, sorry, this should be input current. Input current is equal to inductor current when the switch is on, and input current equal to 0 when the switch is off, because this part is disconnected then. So, you can write the input average quantity is equal to D into average inductor current, where we are ignoring the ripple of the inductor current. Then if we linearize, if we take this term, so we can again write input voltage average is sum of the DC plus perturbation, input current sum of the DC plus perturbation due to ratio, inductor current, then V2 voltage. Then what can we write? If we write down this expression, what we will get? This, where we have ignored, what we have ignored here? Here we have ignored D perturbation and V in perturbation. This part was ignored, the ignored term. Similarly, here we have ignored D perturbation into IL perturbation. So, this product of these perturbations are ignored because these are the nonlinear term, and since we are assuming the perturbation to be very small compared to their steady state value, so product of perturbation will be even smaller. So, you can drop them. Now, with this approximate model that we have obtained, we can draw the equivalent circuit. So, V2 was our original V2 average, which was the terminal 2, right. So, this voltage is nothing but D times this voltage, which is nothing but this voltage, and D times this voltage, and they are added up. So, we are getting this one, and the input current, which is this current, right. This is the sum of this current, which is nothing but this current, and this current, which is nothing but this current. Okay. So, they are all positive signs. So, they are in parallel current path, right. Now, you say these two switch we can replace with this transformer model, and then rest of the circuit will remain same. That means, this 3 terminal PWM switch model we can write in terms of a DC transformer and also dependent voltage and current sources. Now, for a buck converter, this switch model we have already found. Now, we want to place it with this inductor. So, this part now we can join back, and beautiful thing, if you incorporate a current load, you can also incorporate here current load. If you incorporate a current load, if you incorporate the additional impedance or the filter element, the same model only will not touch this part as long as you do not change anything, then we can update this right side of the switch model without rewriting the equations, and that is somewhat special in this technique compared to state space averaging, where we need to rewrite all the equation every time when we add any dynamic element. Now, in case of the average model, we discuss the waveform averaging technique. If you recall that we initially consider the waveform of capacitor current, input current, inductor current, output voltage, capacitor voltage, and we obtain the equivalent model by averaging the waveform over a periodic cycle, and we got 3 model, one for the input current, the other for the inductor current dynamics, and the third one for the capacitor voltage dynamics. So, in this technique we can put them 3 circuits side by side, and you see these two, there is a we can replace with a DC transformer, and here since there is no ESR, we can simply connect these two terminal. So, we will get the overall circuit like this by putting a DC transformer. So, this model is also same which we obtain by using a 3 terminal switch model. That means, if we use an average switch model or if we do waveform averaging by using circuit averaging, so we will get the same equivalent circuit model. Okay. So, the equivalent circuit model can be obtained either by applying average switch model, that means the 3 terminal switch model, or you can obtain by individually considering individual waveform and their sub interval equation and then average out, or basically sub interval waveform we can take and then average out to obtain the dynamics of the variable that we are interested in. Similarly, we can do we can apply this circuit averaging technique in a boost converter. Here we can consider again the 3 terminal model, where input side switch which is connected to the inductor is basically the input voltage is discontinuous and the current is continuous, because we have an inductor before this. Output side, since we are not considering ESR, output side is connected to the capacitor, and which is the voltage is continuous, but the current is discontinuous. So, input voltage can be written in terms of output voltage when the switch is off, and we can take the average input voltage is nothing but 1 minus d into average output voltage. Similarly, the output current is nothing but the inductor current when the switch is off, and it is 0 when the switch is on. So, you can write the average output current is 1 minus d into average inductor current. Then using the same method, if we replace this quantity to be V1 plus V1 hat, and we can replace d equal to capital D into d hat, and this quantity to be V0 plus V0 hat, then we will arrive this equation to this equation by ignoring the term d hat into V0 hat that we have ignored. Similarly, from this equation we can write this equation where we have ignored d hat into I L hat that we have ignored, right. Then we have this two approximate equation where we have ignored their nonlinear part of term and we can draw the equivalent circuit. See, this is the input voltage. If you look at this voltage, it consists of two terms, one this voltage minus this voltage. So, if you come from this to this side, it will be V11 minus plus this term is equal to this term, and that is exactly what. If you take this term to this side, then V1 plus V1 hat whole thing plus d hat into V0, that means from this circuit, is equal to this term. Similarly, if you write the current, the output current consists of two parts, this part minus this part, and this is the minus part. That means, the current is going in this direction. So, this current minus this current will be our this current, right. Now, from this two terminal, we can represent in terms of a DC equivalent, like a DC transformer, where the ratio will be 1 minus D into 1 is to 1. And these are well known standard technique, but this is just for sake of deriving small signal model. These steps are important, that is why I am showing. Next, in the boost converter, we have obtained the equivalent switch model, the average switch model. Now, if we incorporate this average switch model to our original boost converter, where we have obtained this model, then the full model can be obtained, where we just plug in the inductor in the left side and the capacitor in the right side with the load. So, we will get the complete equivalent circuit of a boost converter, and this is an ideal boost converter. In case of, if we repeat this thing using a circuit averaging technique, that means what we did was the average switch model. So, in this approach what we did, we started with a boost converter. If you look at very carefully, we have first So, we have first extracted the switch part of the boost converter. That means, we took the switch element and we have not touched anything like left side inductor, right side capacitor, that part we kept as it is, and we have just extracted the switch model, and then we obtain the equivalent circuit of the switch model, and then we have connected the inductor and capacitor of the original boost converter, including the switch model, we get the complete equivalent circuit. Now, can we do the same thing without using switch average model? That means, without using average switch model. How to do that? So, we take a boost converter, and if we take the average inductor current. So, what is the inductor current of a boost converter? DIL dt, instantaneous inductor current. It is equal to V in by L when S is on, and it is equal to V in minus V 0 by L when S is off. That means, if I take the average, because here taking L left side, if you take, or if I write L into this, hold on, if I erase this part. So, this is nothing but V in, and this is nothing but V in minus V 0. So, if we take the average of this inductor current over a cycle T, that means that I am talking about average inductor current, then the derivative of this average inductor current is nothing but this term. This will be nothing but d times average of this and 1 minus d time average of this, and since input is common, so it is simply average of inductor current input voltage minus 1 minus d into average of output voltage. Then we can again write that we know that any quantity we have already discussed can be replaced by its steady state quantity plus part of quantity, and that we did for all the terms we have repeated. And we know that the derivative of steady state quantity is equal to 0, and that is why we got from this step to this step. And this is one equation which is the part of dynamics of the inductor current, which is derived using the average behavior of the boost converter over a periodic switching cycle T. And here we can write down, we can from this equation we can draw the equivalent circuit, that means L di L dt. In fact, you can consider this model itself, plug in. This will be the dynamics of this inductor, which is the current dynamics, basically current. This is equal to V in minus this term, that means if I take this particular term, this is here, minus, it is divided into two parts. One is 1 minus capital D into this, which is this term, that means I am talking about, if I take this term product with this, and the other quantity is this, in which we have ignored, that means there was minus the plus d hat into V 0 plus V 0 hat, that is approximated to be V 0 into d hat, because we have ignored d hat and V 0 hat, this we take as a 0. So, we obtain this circuit. Next, let us, if you derive the capacitor current equation, capacitor current is nothing but average is C into dV0 dt. Here, since the capacitor there is no ESR, the capacitor voltage is same as the output voltage. So, you can take the average voltage and its derivative, and you can see for the boost converter, the capacitor current, instantaneous capacitor current is minus V 0 by R when S is on, and it is I L minus V 0 by R when S is off. So, that is why if you take the average capacitor current, this term and this term is common. So, it is simply average quantity, and this is d in 1 minus d into I L. And again we expand this average quantity with their steady state quantity plus perturbation. So, you can write down this expression, and if we ignore the product of perturbation, then we can write down that the derivative of this term will consist of this term which is here minus this term which is going down, and then minus V 0 by R, which is nothing but this voltage by resistance which is going out. So, we got, now we can write input current. For input current of a boost converter, it is same as the inductor current. So, you can write all three equations, that means input current and inductor currents are same, and we already got the dynamics of the inductor current, we already got the dynamics of the capacitor voltage, and we join them, then we can replace this with a DC transformer, and then we can obtain this. And you will find this equivalent circuit is same as the one which you obtain using average switch model. The same thing can be obtained by circuit averaging technique, by averaging the waveform over a periodic cycle. Now, the same technique can be used for a buck boost converter, where when the switch is on, you will get one set of circuit when the switch is, and you can write down their voltage, inductor voltage expression, then in the capacitor current, and you can write down their average dynamics, okay? Average voltage, average current dynamics. That means what we did for the circuit averaging technique, that means this is we are doing averaging the waveform. Then we can take the second switch configuration, and we can write down the derivative of the inductor current in terms of their average current quantity, where we have ignored the ripple of the output voltage and the ripple of the inductor current. Then we can write down the inductor current average dynamics, which is the dynamics over the cycle, and output voltage average dynamics over the cycle, and we can write down the input current average dynamics. Okay? Then from this expression, we can replace this average quantity by their steady state quantity plus part of quantity, and then write down the equations again, and we should ignore, this should be capital V in, ignore the product of perturbation term. Okay? So, with this we can also obtain the capacitor current dynamics here, which is C into dV0 dt, part of capacitor current dynamics and also part of input current dynamics. And next, if we consider the inductor part of dynamics, we can draw the equivalent circuit. Here it is very straightforward that L di dt is equal to dV in, and this is capital V in L di dt. This is added, right. So, that means, if we take L di dt, we will get this quantity minus plus this quantity. So, that means, it is added, and then plus this quantity which is here. Okay. Similarly, if we take the part of voltage dynamics, so part of voltage dynamics, this is nothing but the capacitor current part of dynamics. The capacitor current which is positive when it is coming in, that is equal to minus of this, which is this term, that means, it is going out, and minus of load current which is also going out, plus of this current which is going in, right. And we can also draw the equivalent circuit of the input current, which consists of D into IL, this is by IL perturbation, plus I into D, which is this term. This is average inductor current. Now, we can write down all this inductor dynamics, capacitor dynamics and the input current and their corresponding circuit that we have drawn already. So, this we have obtained for the this all will be capital, we have already obtained, and 3 individual sub circuits are the part of dynamics corresponding to 3 individual, like a inductor current, capacitor voltage and the input current. Then we can club together all these 3. This is the 3 equivalent circuit, and then we have to collect these 3 terms. The first term is the input current, then the second term is the inductor current, and the third term is the output voltage. And you see, in between these two, we can represent using a DC transformer, the same thing here also, and if you do that, this can be replaced by a DC transformer and this can be replaced by a DC transformer, and we can get the complete equivalent circuit of a inverting buck boost converter, and that can be easily derived using circuit averaging technique. So, with this, in this lecture we have discussed circuit averaging technique, which there are 2 techniques. One, we can use obtain the equivalent circuit by averaging the waveform over a periodic cycle, and the second approach, we can obtain the equivalent circuit by applying average switch model, like using 3 terminal switch model. And we saw that both the technique result in the same equivalent circuit. Then from that equivalent circuit, we can extract the AC part and the DC part. So, we obtain the small signal model with certain assumptions, that means the perturbation is much smaller than, magnitude is much smaller than its average quantity, and then we derive the equivalent circuit of switch mode power converter, and we derive it for buck boost as well as buck boost converter. So, with this I want to finish today's lecture. Thank you very much.